Welcome back. This video is all about calculating energy release from fuels. So it's looking really at exothermic reactions. Really useful for GCSE and A-level chemistry. It's also a revision for little bits of physics as well. But this video is also catering for the Btec level 3, unit 3 specification when we look at fuels at section G. So we have to know a little bit of background of alcohols, and you should know, especially if you are post-16 and you're in sixth form, that alcohols have got, as a revision, a functional group of OH. So it's an oxygen and a hydrogen. And we should know that for every carbon, so for n number of carbon, we have double the number of hydrogens plus 1, and then we have the OH functional group on there as well. So that's a little bit of revision. We've got methanol, ethanol, propanol, butanol. I think you just pause this video for a second and just write down those formulas and what they might look like. And once you've done that, you should come out with something a little bit like this. So methanol there, if we remember, we're using this formula here of CnH2n plus 1. Methanol have 1 carbon. Because it's got 1 carbon, we need to double that 1 plus 1, so 2 times 1 plus 1 is 3. So the so around the carbon there will be 3 hydrogens, and then an OH on there as well, and that would look like something. As we have our carbon there, we have the hydrogens around it, and then that OH functional group. Ethanol, C2, remember the hydrogens, we need to double it plus 1, so that's going to be 5. And we have our 2 carbons with our 5 hydrogens around it, and then our OH functional group. Propanol, we've got 3 carbons. If we have 3 carbons, we double it plus 1. That's going to be 7 hydrogens. So we've got 1, 2, 3, and then 3, 4, 5, 6, 7 OH. Butanol has got 4 carbons, so it will have 9 hydrogens and OH. So 1, 2, 3, 4. And then there's our 9 carbons around it. Now, to do these calculations, we've got to be familiar with these following equations. The first equation here, with Q equals MC and the change in temperature, you might also recognise that from your specific heat capacity calculation in physics, and sometimes that Q just might be an E. So what we've got here is the energy, the thermal energy transferred within a system is equal to the mass times the C, which is the specific heat capacity. Remember the units there, joules per kilogram degrees Celsius. And then we've got delta T, which is the change in temperature. So we're going to need that calculation in just a minute. But for the heat capacity of water, normally be given to you, but it's 4.2 joules gram degrees Celsius. So that's a handy one to remember. And then we've got the number of moles in this equation here, which is when we want to get the moles of the fuel that we're burning in these calculations. So how many moles of fuel that's been burnt is equal to the mass of the fuel burnt. So you need to know the before and after, a bit like the temperature, divided by the MR, which is the molecular mass. And we also need to know what energy, for the energy being released, That's equal to this here, look, it's the thermal energy transferred divided by the moles of the fuel burnt. And that will give us our answer in kilojoules per mole. So if we want to look at the MR just for a second, we can flick back here, and for that we need to know the ARs of all of the atoms inside our alcohol. So carbon has got a mass, that's an AR of 12, hydrogen is 1, and we should know that oxygen is 16. So when we look at our fuels here, we know here that methanol has got 1 carbon, it's got 4 hydrogens altogether, and 1 oxygen. So to work out the MR of methanol, we need to do 4 times 1, which obviously is going to be 4 with hydrogens, plus 12 plus 16. For ethanol, we've got 2 carbons, so it's 12 times 2, plus altogether 6 hydrogens, because we've got 5 here and 1 there. So it's 1 times 6, plus the number of oxygens, so there's just 1, it's 16. Have a look at these, have a go at doing the other 2, and see if you can pause the video and see if you can work out the MR of each of those 4 fuels. Once you've done that, we should know that methanol has got 32, so it's 32 grams, so 32 grams of methanol be 1 mole. Ethanol, we need 46 grams of 1 mole. It's 60, I believe, my head there for propanol, and butanol, 74 grams. So let's have a look at a worked example. In this example, we're going to use a spirit burner filled with butanol. Now, we're using that to heat up a boiling tube with 20 centimetres cubed of water, and we're going to record the temperature at the start and then stop the experiment, stop that spirit burner once that temperature rise has reached 20 degrees. So once we've done that, we can look at all of the information that we need to know. So we need to know for this the mass of the H2O. So the mass of the H2O. Now, mass is obviously in grams. We've got 20 centimetres cubed there, but we should know that 20 centimetres cubed is 20 mil, which is also equal to 20 grams. So we have that. Now we also need to know the temperature change as part of our equation a bit later on. That's going to be 20 degrees, because that's how long the spirit burner was on for. And we need to know the heat capacity of the water that we're using in there, and that's 4.2 joules per gram degrees Celsius. Once the spirit burner was done, this was a real experiment, and the mass loss of the fuel was 6.25 grams. So when we put this into our calculations here, the mass was 20 times 4.2 times the change in temperature, which is 20. When we do that, we know that is 1,680 joules. Now for this calculation, it's here later on, it's all going to be in kilojoules. So we need to convert this into kilojoules, so we need to divide that by 1,000. Once we've done that, we know that it is 1.68 kilojoules. So during this experiment here, we transferred 1.68 kilojoules worth of energy to the water. We can then look at the number of moles that was was burnt in this experiment. And so by doing that, what we need to do, we need to get our MR. We need to use our MR of butanol, which we worked out before. When we go down, it is 74 grams. So we're going to use this figure here to help us out. So moles there, MR, let's put a little note there, is 74 because it's 74 grams. Now to work out this calculation, it's going to be the mass divided by the MR. So to work out the number of moles, it's mass divided by MR. Again, that's a GCSE calculation. The mass loss here was 6.25. And we'll divide that by 74, because that's our MR of butanol, which gives us 0.08 moles. So during this practical here, where we heated up the water, 6.25 grams of fuel was burnt to heat up the water by 20 degrees Celsius, which is equal to 0.08 moles. Now what we can do for that, we can do two calculations. We can then work out how much energy was released in kilojoules per gram. All right, so we can do that in kilojoules per gram. And we can also look at kilojoules per mole. So for our kilojoules per gram, we can use this one here. So that's 1.68 kilojoules. And then per gram, so it's 6.25, we can use that one. So 1.68 divided by 6.25, which gives us, I believe, trying to do two things at once here, calculated 0.26 kilojoules per gram. Yep. So we've got our energy in kilojoules, energy released divided by our mass. Now for this one here, once we get it in kilojoules per mole, we need to use our Q again. So it's going to be Q divided by the moles, just there. So our Q, so I change pen. Our Q was 1.68 divided by the number of moles, which was 0.08. So 1.68 divided by 0.08. We're going to have an answer of, I think, just lost it from the calculator now. Around about 21, I believe, kilojoules per mole. Now, this is burning, it's combustion, it's an exothermic reaction. Because it's an endothermic reaction, it's worth remembering that in a reaction, when energy goes into a reaction, it breaks bonds. When energy is released, like in combustion, so energy out, it's when bonds are formed. So in an exothermic reaction, we've got more bonds that are formed than are broken. So more bonds that are formed than are broken, and that's simple combustion. And because it's exothermic, really, we should have a little minus sign there. Anyway, I hope that's been useful for you as a bit of a refresher on how to calculate energy release from fuels. Thank you. Good luck.